So welcome everybody, wherever you are in the world, to our webinar. We see we have a number of people from across the world. Today's webinar is called Nature's Stone, How the Body Balances Calcification to Bone While Protecting Soft Tissue. Our speaker today is John Schoenecker, and John works in a whole host of areas that are now very important to PXE, given some new findings that maybe some of you heard about last week in our webinar with Karen Van de Vettering. John is the Assistant Professor of Orthopedics, Pediatrics, Pathology, and Pharmacology at Vanderbilt University in Nashville, Tennessee. And we're going to turn the presentation tool over to John right now, and he's going to give a presentation. At the end of the presentation, we will take questions, but we welcome you to write those questions anytime you want. So on the right-hand screen, you will see a box that says questions, and you can type your questions into that box. You can write them anytime you want. I will be collating them throughout the webinar, and at the end of it, I will ask John the questions that you all have written. I'd like to announce to everyone that, yes, we are archiving this presentation, so both the slides and the video, the audio will all be available on our site. We'll reflash that URL later. And we will be able to give you access to that shortly. It usually takes us about a week to get that up and going. Okay, so without further ado, John, I'm going to turn it over to you.
Sounds great. First, I'm just going to quick ask, you can hear me, correct?
Yes, and we're...
Wonderful. All right,
okay.
And you can see my presentation, so we're all set?
Yes.
Great. Well, thank you, everybody, for this opportunity to talk with you today. The goal of this presentation is to explain our current understanding as to how our body directs mineralization or calcification to bone while avoiding mineralization of soft tissues to tissues such as skin, muscle, etc. So let me see if, okay, here we go. Before we dive into these incredible mechanisms, we first must take a big step back and take a broad look at science. Almost every substance in the universe is made up by small particles, as shown here. As you probably have heard, these particles are called atoms. And together, these little atoms combine to make the building blocks of the earth, trees, rocks, air, water, and so on. Importantly, there are very small variations in these atoms, making them different. Each different atom is called an element, such as hydrogen or helium, as shown here. There are over 118 elements that we know of, but almost 90% of the Earth is made up of only 10 of these elements. And more impressively, 98% of our bodies are made up of 10 of these elements. Although elements make up almost everything on Earth and our bodies, it's important to realize that they rarely exist as a free element. Instead, elements combine, as my son likes to always say, like Legos, with other elements to make bigger structures that we call molecules. For example, if we take hydrogen, the element, and oxygen, the element, and we provide two of these hydrogens with one oxygen, we make water, which is a liquid at room temperature. Or if we combine two oxygens, as you see here, we make air, or oxygen, which is a gas at room temperature. More complex if we add calcium and the molecule called carbonate, we make limestone, or calcium carbonate, which makes up much of the rock and is a solid at room temperature on Earth. Thus, the Earth and us are made up of building blocks working from atoms, which are elements, which combine to form molecules that are either a solid, liquid, or gas, which define us. In regards to the molecular problems of PXE, let's consider two very important building blocks of man: the element calcium and the molecule phosphate, as shown here. Calcium and phosphate are essential for most biological processes of our body. Specifically, they're absolutely essential for the function of cells within our body. If we look closer at the cell and why calcium and phosphate are important, calcium, which again is an element, is required to translate events that happen outside of the cell to processes that occur inside the cell. They are essential for what's called cell signaling and allow a cell to respond to anything that happens outside of the cell. Phosphate, on the other hand, is often stacked together with a molecule called adenosine. Usually we have one adenosine to 3 parts phosphate, and you'll often hear that called ATP. The best way to think of ATP is it literally is the battery of a cell and is used to power most cellular functions. Thus, calcium is essential for signaling from the outside, and phosphate is important to make that battery, to make it so that the cell can be powered. Additionally, and most importantly for PXE and for an orthopedic surgeon such as myself, is calcium and phosphate can combine with each other to make much bigger structures, as seen here. These are crystals at room temperature. The main crystal that it forms that we care about is called hydroxyapatite, which is literally nature's stone. That hydroxyapatite is what you see here in these bones, and it is made up of that calcium and phosphate, and allows us to stand against gravity and allow our muscles to work on these bones to move them. Because of the essential nature of calcium and phosphate for cell function, their distribution in our body is very tightly regulated. Importantly, there is typically over 10,000 times more calcium and phosphate circulating in our blood as opposed to what is inside of a cell. Now, this is great for cell function. Because of all of that abundant calcium and phosphate that circulates around in your bone, it makes it so our cell signaling and our battery always have enough calcium and phosphate to function. However, at this concentration in the blood, calcium and phosphate are essentially at the point when they will spontaneously combine and form crystal or hydroxyapatite. Now, for me as an orthopedic surgeon, that's fantastic because it makes it so that your bone is great. However, realize that at that high of a concentration, that amount of calcium and phosphate also enters into all of your soft tissues and can spontaneously start to form calcium and phosphate crystals or bone within your soft tissues. Now, the things that we typically study in my lab, being an orthopedic surgeon, is how to prevent calcium and phosphate to come together and form what's called heterotopic ossification, which is the development of calcium and phosphate crystals in your muscle, tendons, ligaments, etc. But realize also that this process is continuously happening in all of us, and eventually all of us end up having we succumb to the problems of calcification in soft tissue, hopefully at a much later age. Specifically, the main one that we always try to prevent is calcification of the muscle within our vascular wall, which causes atherosclerosis. Thus, the concentration of calcium and phosphate in our blood is set up to be optimal for cell function and for bone. But this concentration in blood eventually can lead to soft tissue calcification, as seen here. For this reason, the maintenance of the balance of these two element and molecule is absolutely critical. And we have an incredible system that uses multiple organs to allow for continuous regulation of the amount of calcium and phosphate that circulates, in particular our kidneys, the endocrine system, the diet, how much we eat, and our gut, how much we absorb, are so essential for maintaining this balance to make it so our cells work, our bones are great, but that we don't have a lot of spillover into our soft tissues. It's also really important to realize that the majority of calcium and phosphate in our body are actually in our skeleton. 95% of calcium and 85% of your phosphate are in your bones, and therefore the amount of bone that you have is also tightly regulated by these systems, and you essentially want to think of calcium and phosphate as flowing through these systems. So in health, we have a balance of calcium and phosphate that's great for our cell function, both signaling and power. It's great for our bone, and ideally we're at a level that not much enters into our soft tissue, as we see here. If we have too little calcium or phosphate, what can end up happening is that the reduction makes it so that our cells do not work really well. We have poor signaling and poor power. Our bone is hurt because we lose calcium and phosphate in the bone. But this is okay for our soft tissues in regards to developing calcification because there isn't any to spill over into that area. If we look at the other side where we have an overload of calcium and phosphate, that actually can lead to problems of cell signaling because it can essentially make your cells signal too much or be on the edge of doing things they shouldn't do, as seen here. It's fine for bone. It typically ends up building up tons of bone, as seen here, but this can lead to problems in which there's a lot more calcium and phosphate that enter into our soft tissue compartments and make it so that we start to have lots of calcium and phosphate develop into crystallization or bone within our muscle. Because of the near saturating concentrations of calcium and phosphate in blood, even in health, we have calcium and phosphate which enter into those soft tissue compartments and can potentially start to cause calcification of these tissues. Again, this is happening to all of us, and over time all of our soft tissues will start to deposit calcium and phosphate within it, again most notably in diseases such as atherosclerosis. And so even when we have really good balanced kidney function, endocrine function, diet, and gut, we have calcium and phosphate at high concentrations that enter into our soft tissue compartments. For that reason, the main thing that my lab studies in this process, as well as the wonderful other researchers in PXC International, is what are the mechanisms of protecting the soft tissues from calcification. To be effective, soft tissue protection must inhibit calcium phosphate formation, but also allow protection of bone. So the key question, and what I would like to explain here, is what are the known main mechanisms of protecting our soft tissues from spontaneous calcification? The answer to this, and the main one we'll discuss today, is a molecule that's called pyrophosphate. Pyrophosphate is made of phosphate and oxygen. Specifically, we have two phosphates to one oxygen that forms the molecule pyrophosphate. This molecule is excellent at preventing calcium and phosphate from combining, forming that crystal structure called hydroxyapatite. Thus, it's excellent at preventing soft tissue calcification. So with that, the question comes down to, in terms of the disease PXE, what is the main source of pyrophosphate? Well, to understand this, let's go back to the battery idea, and ATP, which again, if you remember, is an adenosine with 3 phosphates. Well, that ATP can be broken down into an adenosine with 1 phosphate, releasing those 2 phosphates, forming pyrophosphate. Now, if you look through the literature, often you'll see it written like this, where ATP is broken up into AMP and pyrophosphate. And again, that's an adenosine with 3 phosphates, which the 2 phosphates are broken away and make pyrophosphate, as seen here, and releasing an AMP. So where this has become very exciting are the breakthroughs in science as to how this system happens. So let's take a cell and let's think how in the world we can get that ATP out into the blood and make pyrophosphate. what has been discovered is that there is what's called a pyrophosphate pump. With that, there is a protein that transports ATP from the cell out into your blood. And immediately on the surface, there's an enzyme that breaks that ATP down into 1-AMP and a pyrophosphate, as seen here. So essentially, the best way to think of this is that the cells will sense the amount of pyrophosphate that's needed. They pump out ATP, which is immediately transferred into AMP and pyrophosphate, thus leading to circulating pyrophosphate. Now, the big exciting breakthrough in regards to PXE is that what we now know is that ABCC6 and EMPP1, which are these two systems that make up the pyrophosphate, is that ABCC6, as you probably know, is the main thing that's missing in PXE. With that, in theory, what we think the breakthrough in this disease is we have an insufficient amount of ATP sent out into the bloodstream to be cleaved into AMP and pyrophosphate. Thus, we think that there is less pyrophosphate circulating in these patients, leading to soft tissue calcification. Another disease called calcified arteries of infancy is a deficiency of the cleavage or the enzyme that cleaves that ATP into AMP and pyrophosphate. So let's see how we put this all together. If we go back to our circulating calcium and phosphate throughout the blood, that wonderful pyrophosphate pump adds pyrophosphate into the circulation and allows it to go around without calcium and phosphate. That pyrophosphate can enter into the soft tissue compartments where it's excellent at preventing the formation of crystals or hydroxyapatite and serves to protect soft tissues against that problem. Now, what's really neat about this is that, yes, that pyrophosphate also enters into bone, which at first you would think would be terrible for somebody like me as an orthopedic surgeon, because then everybody would have really bad bone because that pyrophosphate would make it so your bone can't form. But your bone has a wonderful enzyme called alkaline phosphatase, or AP as denoted here, which as soon as it comes across that pyrophosphate, it zaps it into two phosphates, and these phosphates actually get used to make more bone. So in our bone, we have lots of alkaline phosphatase, and as pyrophosphate comes in, it actually takes that pyrophosphate, and instead of it making it so you can't make bone like what happens in soft tissue, it actually uses that pyrophosphate as a source of phosphate to make more bone. And thus, the pyrophosphate system has what we call tropism, or it directs itself to protect against crystallization in muscle, where it actually can, in a sense, if there's good alkaline phosphatase, promote the formation of bone. If you really think about this, it's a beautiful system. Therefore, if we think about these two diseases, PXE and CAI, they both are known to have problems with the pyrophosphate pump. Essentially, it's gone. With that, they should lead to a decreased amount of circulating pyrophosphate as seen here, which, if that's reduced in the soft tissue compartment, can lead to, in theory, development of calcification within all of that soft tissue. It doesn't really affect anything in bone, as that pyrophosphate, unless other sources of phosphate become really low, isn't really the main source of phosphate for the development of bone. So the question with all of this new information we of course have is, how in the world do we fix this? Well, the most straightforward way to optimize this system, if you think about it, is to make sure that our diet, our kidney function, our endocrine function, our bone, and our gut are all optimized to make it so that we do not pour extra phosphate and calcium into the soft tissues, overwhelming the circulating pyrophosphate that we have. That overall is probably one of the biggest keys in my mind that we need to make absolutely certain we do with patients with PXE and CAI. Of course, you probably have heard of the trials of magnesium. We don't completely understand how magnesium plays a specific role in this. What we do know is, most importantly, is diseases, especially as we do with mice, where we lower the amount of magnesium that's available, can definitely lead to problems of having calcification in soft tissues. What we're trying to learn is that if the opposite of that is true, if we provide a lot more magnesium, does that help protect that soft tissue from calcification? Does it add protection that hopefully we find less pyrophosphate does not provide? The other thing that researchers are doing right now, and is really exciting, is the idea of using our newfound science of how to fix specific proteins. Could we potentially fix that pyrophosphate pump? Is there a way we could make it so that we increase one of the other proteins that causes ATP to go out into the bloodstream to make up for the loss of ABCC6? Or is there a way that we could genetically fix the problem with ABCC6? Now, this will be a little bit difficult in the sense that there are many different mutations of ABCC6, which means that if we attack it without completely restoring a new ABCC6, probably almost every patient will be different. Now, that being said, one of the other big things that has come up, and you will hear a lot about this, especially in the literature over the next year or two, is the potential of using what's called bisphosphonates, a drug commonly used for osteoporosis, to help fix this problem. For this reason, I thought I would go into a little bit more detail as to why people are thinking this, or the rationale. So, in order to understand this, let's go back to that molecule that we call pyrophosphate, which again is a phosphate, an oxygen, and a phosphate. What we know is that bisphosphonates, in which only has one real big change in the molecule in terms of it compared to a pyrophosphate where we substitute a carbon for an atom, they look almost the same and they act the exact same, other than the fact that this molecule is way more stable than pyrophosphate, because when you substitute this element, carbon, for atom, it makes it so that the enzymes that break down pyrophosphate, such as alkaline phosphatase, cannot break this down. So essentially, think of a bisphosphonate as just a very, very stable pyrophosphate. Now, actually, we didn't know this at the time scientifically, but bisphosphonates were first used by humans in the 1800s, put into the water supply to try to prevent the development of calcification of pipes that came from combination of calcium and phosphate to form crystals in our water supply. And then in the 1950s, because it was observed exactly what we have written here, that alkaline phosphatase could break down the pyrophosphate, but bisphosphonates cannot be broken down, we started using bisphosphonates to treat what we thought would be mostly bone disorders. However, the first publications of bisphosphonates, the big breakthrough article, in fact, in Science in the 1960s, actually shows that bisphosphonates are fantastic at protecting soft tissues against calcification, in particular something like atherosclerosis. So the best way to think of it is that if we put bisphosphonates into the system, as you see here, and an important point to know about this is that unfortunately we can't really take these orally very well because most of the bisphosphonates are not taken up by the gut, so they have to be injected. But if we get them circulating, as they go around, they will enter into the soft tissue compartment just like pyrophosphate, and they act just like pyrophosphate in that area and can make it so that you don't have that soft tissue calcification, as seen here. So basically, the best way to think about it is that they are added protection. Now, in my lab, what we're doing right now is, again, I work on a problem in which muscle starts developing spontaneous calcification. As you can see, is this mouse right here in which we've changed genetic parameters on this mouse that make it so that all of its muscle starts to become bone. What's really exciting about this is that with low doses of bisphosphonates we can completely prevent that from happening. So this is a very, very exciting area right now. And so again, if you think about this as added protection, it would make you think that we should jump to this right away. Now before we do, I want to point out a couple of things that we have to make sure that we think about before we jump into this. First is, remember, bisphosphonates love bone. They bind to bone very, very, very fast. For that reason, when we give them in circulation, as they go through your circulation, they very quickly are sucked up like a sponge in bone. So most of them end up accumulating in bone. Now in regards to how they work for osteoporosis, because alkaline phosphatase, or AP, cannot break it down, what happens with bisphosphonates, what we don't think happens with pyrophosphate, is the cells in the bone end up taking it up. And when they take it up, they block specific signaling pathways, and they actually make it so that the cells that break down your bone don't work well, which is why these drugs are incredible to prevent osteoporosis. Because they love to go to bone, they love to bind to all of that bone, they enter the cells in the bone, and they block the resorption of bone. So the thing is that the question that comes up with this is that if we were to give patients with PXE bisphosphonates, we know for a fact that as they go around, they're going to quickly be sucked up by that bone. And the question is, will we have to continuously redose this? And if we have to continually redose this, what does this overall mean for the other parts of our body in which those bisphosphonates will bind to? Understand that the half-life, meaning how long it takes to get rid of half of that bisphosphonate, is 9 to 10 years, which means that if we continually redose bisphosphonates, we will very quickly load up the bone with lots of bisphosphonates in these patients, and if it's causing problems, we won't be able to get rid of those problems for 9 to 10 years. That's how long it'll take for it to get out of the system. Now that doesn't necessarily mean these are bad things. I only bring this up just to make sure that everybody doesn't just throw caution to the wind and jump into this thinking that there are no potential side effects of this idea. Additionally, the other thing to remember is that the principle that these bind to bone is that when we put them in circulation, if the patient already has calcification within soft tissues, just like the sponge soaks it up in bone, we also will have those bisphosphonates go right to that soft tissue, and it will build up in those soft tissues. If that calcification already exists, the thing to understand about bisphosphonates is they do not cause calcification to go away. If they did, we would never use them for osteoporosis because it would make your bones weak. Instead, those bisphosphonates have a tendency to stabilize the bone and make it so it doesn't go away. So the theory of that to remember is if we put bisphosphonates into patients who already have a lot of calcification of their soft tissues, although it might prevent the development of more bone in there, it should not make it go away. And when it's there, we don't know what it will do to the cells in that area. And this is something that we need further research into, as for example, if you get calcification of skin or your retina, for example, is what would the effect of a 9 to 10 year drug be on the cells in that area? Again, this is not to say that I don't think we should consider doing this, but these are the scientific questions that I believe must be answered before we jump and do this. So in summary, in terms of the main principles of what we discussed today, is remember that because of the really high circulating calcium and phosphate in your blood, it's great for the cell, great for bone, but it can be bad for our soft tissue. Because of that, the recent discoveries are this incredible pyrophosphate pump that pumps out pyrophosphate all through the blood, which enters into your soft tissue and protects it. the problems with PXE and CAI as we see it today is that the pyrophosphate pump is inefficient at keeping up, and therefore we lose our pyrophosphate and we end up building up calcification in our soft tissues. So the theories that we have learned is that with the loss of that pyrophosphate pump, we think that there is less circulating pyrophosphate. One of the big goals of the PXE International right now is to prove this. The reason why I say that is that in my experience is everything has dual functions. We would love to look at this diagram I've drawn here and think it is as simple as I drew. But I guarantee you as we go through we're going to find that there are other functions of this pump, and that the problem of soft tissue calcification or that of the retina that we see in PXE patients may not be just because of a loss of circulating pyrophosphate. For that reason, scientifically, we need to set up good experiments that allow us to say yes or no, that is the main problem, so that we can direct our therapy. Right off the bat, one of the main things in terms of the principles of this disease we can do is make sure that all of our patients have really good functioning balance of their diet, their kidney, their endocrine, their gut, and their bone, to make sure that we're not going through waves of increased calcium and phosphate in our blood into that soft tissue, which can end up causing calcification by overwhelming, in theory, that pyrophosphate. And the big one that's coming around the corner right now, despite some of the negative aspects I brought up, is that the theory of using a bisphosphonate to make up for the loss of pyrophosphate, if indeed that's what causes this disease, is very exciting, in particular with what we already know that we can do with these drugs. The main thing we have to figure out is what the long-term effects of using bisphosphonates over and over and over would be on these patients. So in summary, I hope you understand through this is that the element calcium and the molecule phosphate and how they interact with each other is the main issue that we have in PXE, and we have a lot of really exciting science that's happening right now that can allow us hopefully to come up with very targeted pharmaceuticals that can make it so that these patients do not have the devastating consequences of having calcium and phosphate combined in tissues that they shouldn't. The other aspect of this that's so exciting is that through this research, it's my belief that we're going to find incredible new therapies that in the long run can make it so that it is not inevitable that as we age, we develop diseases of soft tissue calcification such as atherosclerosis. We have a lot of other exciting things that we have happening here in our lab. One of the big things that I would love to talk with you about at another time is how so much of this process is directed by injury, and it's something that we can talk about in another session. But with this, I thank you very much for this incredible opportunity, and I look forward to any of the questions that you might have.
Great. Thanks so much, John. And I hope our audience today and those who listen to this recording appreciate, and I bet you do, what a phenomenal teacher John is. I couldn't wait for this webinar. Ability to explain things is just so wonderful, and I really appreciate it for our people. So we do have a couple questions, and to remind folks, there's a question pane, so a window on your right-hand side usually on the Go to Webinar window, and you can type your question in there. So the first one, John, please clarify the ABCC6 gene in PXEers. Are we missing something in that gene, or do we have a mutation in the gene that causes PXE manifestations, specifically calcification?
That is, am I back on?
You are on.
Great. Can they still see my slides?
Yes, they can.
All right, so let me go to that slide then. Okay,
yes.
Great. Okay, so the question is fantastic. To answer your question, the answer is yes, yes, and yes. And what I mean by that is that the unfortunate part about PXE as a disease is that there are many different ways that you can get it. So for example, you can have it where you don't have the gene really is not made at all, so you don't make any of the ABCC6, and so it never goes to the surface and you don't have that ATP transferred as you see here. Now other people have what's called a polymorphism, which is just a genetic sequence that's mutated that makes it so the protein doesn't function as well. So you would have less ATP being passed through. So the thing is that that's one of the big goals right now of the research, is to try to define every way in which PXE develops. And again, for the most part, what I would tell you is just about everybody is different. They either don't make the gene at all, or they make some of the protein, but it just doesn't function as well. The same is true for diseases such as Duchenne's muscular dystrophy, where the exact same process happens, is that some of those kids don't make that gene at all, whereas others do, and the protein just doesn't function as well.
Great, thank you. Next question, is it possible to artificially administer pyrophosphate?
So that's a great question also, and the answer to that question is that not through the gut, is that just like the bisphosphonates is that it's really difficult to get it through the gut because the gut has a tendency either not to take it up or it zaps it and automatically cuts it up into 2-phosphates. You can give it intravenously. The problem is, again, is it would be something you would probably have to give continuously, because it's so susceptible to being broken down by alkaline phosphatase. One of the big things that we're actually working on as well with that question is, let me change this slide real quick, I'll go to this one right here, is that if you look at this, alkaline phosphatase also circulates in your blood, and you'll see that in the literature listed as TNAP, which stands for tissue nonspecific alkaline phosphatase. One of the big areas we're investigating right now is this, is there are inhibitors, meaning medicines that will block TNAP, and the idea would be is that if we could give those drugs, which are stable and last for a while, could we decrease the activity of the alkaline phosphatase that circulates in your blood, not in your bone, and make it so that we allow pyrophosphate to live longer.
Great, thanks. Is there a role for vitamin K2 in this process? There are some healthcare providers talking about K2's role in the transport of calcium out of soft tissue and into bone.
Great question. And so with that, what we know from our experiments right now is, unfortunately, we don't think so. I've done some of those experiments myself in regards to muscle calcification, and here's what I can tell you. The reason why vitamin K is so unbelievably important is that as your liver makes, there's about 8 proteins in the liver, and then there's about 8 proteins, half of which are in muscle, for example, and the other half are in bone. What vitamin K does is it modifies those proteins so that it can bind calcium. Now, the proteins in your liver that are really important for that are proteins that are important for clotting your blood. The reason why that's important is most people have heard of a drug called Coumadin or warfarin. What that does is it blocks vitamin K, and it makes it so your clotting proteins don't work. With a lot of that, the other proteins in muscle that are vitamin K dependent are good for binding calcium and shuttling that calcium out of the muscle. Whereas the vitamin K proteins in bone grab onto that calcium and keep it there so that it can make bone. We, in theory, thought that those vitamin K proteins in soft tissue would be awesome targets for this disease. However, unfortunately, what we're starting to find is that they're not as important as we thought they were. So, for example, if I take mice and I remove all of the vitamin K dependent proteins from muscle, they do not all of a sudden start developing bone in their muscle. The converse has also been true, is that if we give more vitamin K to mice that develop calcification in their muscle, it doesn't block it. So unfortunately, and I always like to tell people this is the answer today, it may change later, right now I don't feel like that the vitamin K pathway is going to be the main pathway we use for PXE.
Great, and to remind people, we had probably 3 years ago a vitamin K webinar that I'm sure is in our archives, where Pete Borst, who is the senior investigator with Kern, said, "Eureka, I have found it." And so for each of these findings, we're pretty cautious, although we're certainly bullish on making sure that we get to the bottom of it. So next question, I'm going to combine a couple of so just to follow up here, is the vitamin K pathway the same as the K2 pathway?
Yes, it is.
Okay. And then I'm going to combine two questions now. One question's asking, does this in general mean that PXEers should avoid milk and calcium-rich food? And John, a little historical background that I'm sure you've seen, there certainly was some recommendation now 30 years ago that PXEers should drastically reduce their calcium because of one case study that actually didn't have very rigorous measurement. And the other part of the question will be, so where do you think the diet question will lead to? What's the possibilities in diet to control PXE?
So those are wonderful questions. And to start off with, the one main thing to understand about the regulation of calcium and phosphate, as I go back to this one slide, I'll put this up, which will help out a lot, is that if you have a really good gut, kidney function, and endocrine system, it's pretty good at handling big changes in the diet. And so the main thing in terms of that question comes down to, if you have a patient who you know has poorly functioned kidneys or an endocrine system that is off, or also GI problems in terms of calcium and phosphate regulation, they, by far, are the most sensitive to having too much calcium and phosphate, leading to disease problems. So that's one of the first things to think of, is that I think it's not a bad idea for these patients to occasionally have screening to make sure that they don't have those problems. Now, what we are learning, and one of the best areas that we're picking up on this, is many of you might have heard about the recent findings about giving calcium and vitamin D to women in order to prevent osteoporosis. And what one of the big findings was in those studies is that many of those patients, they felt that the calcium and vitamin D that was given, especially if they also ate a lot of calcium and vitamin D in their diet, was so much that it was driving atherosclerosis, even though it was also making good bone. And so those are the type of situations right away in terms of diet that I think needs to be considered by patients who are susceptible for developing calcification of tissues, such as patients with PXE. Is the very first thing I mean by diet is so many people like to take multivitamins. Well, if we have patients with PXE, what I would suggest that I think is safe right now is to take an overall assessment of how much calcium and vitamin D that you take in your overall diet, and try to maintain that level in your diet. So for example, what I always tell my patients overall, what we know with mice is this: if you eat the same thing for breakfast and the same thing for lunch, and you have dinner be your fun meal where you get to change, you can really figure out how much calcium and phosphate and vitamin D you take in a day, because you're only leaving one meal to a variable. If you do that overall, you can make it so that you have a much more balanced calcium and phosphate daily. If you go on binges where you eat tons and tons of spinach over the course of like a week or so, you can make it so that you're giving yourself these phases where you have a much greater increase of calcium and phosphate circulating. And just in general, even if you don't have PXE, we know from all of our animal studies that that variation is not great for your body, period. So the thing I would recommend from where I brought all of this up is make sure endocrine, kidney, and gut's okay. But with the diet is what I do believe is we should be absolutely certain that our patients with PXE are not taking big calcium supplements with vitamin D. And the reason why vitamin D is important is what vitamin D does is cause bone turnover to make it so calcium and phosphate circulate. And if we avoid that, as long as we're getting enough calcium from our regular diet, I think that that's probably the best balance that we can go forward on.
Great, thank you. And just a tiny clarification, does vitamin D help with the absorption of food or other prescriptions?
Yes, definitely. So that's the other part of it too, is vitamin D regulates the gut in terms of its uptake of calcium and phosphate. So, and it's processed by the kidney, which is why so many diseases that you'll see is if you have a gut or a kidney problem, typically you also have a vitamin D problem, and that ends up leading to problems with bone or soft tissue calcification.
And then just a follow-up to that, so there is one PXer who's infamous to us in some ways because he drinks a gallon of whole milk every single day. What do you think of that?
Well, like I said, if he has great function in terms of his endocrine system, his kidneys, and his gut, more than likely he's going to be fine. The thing is that if you start to have variations of those systems, that's where I think that basically can feed this entire process forward.
Okay, so question whether or not you're willing to make recommendations about vitamin D and anything else.
I wouldn't do that on this webinar. What I would want to do is have it something that we could provide, and what I would do is being an orthopedic surgeon, I for the most part take care of surgical problems, and what I would do is talk with my endocrinologist to give the exact numbers just so that I don't give the wrong information.
Question, if ATP can be removed from the cell, cannot be removed from the cell because of problems with ABCC6, does the excess ATP inside the cell cause any problems?
So I absolutely love that question, and whoever asked it, boy, are they paying attention. That's an incredible question, and it's actually one that I think Dr. Lee and Dr. Weedo's group have really gotten into. The answer to that question is I think absolutely, and I think what tends to happen, what I don't have drawn here, is that the ATP buildup inside of the cell ends up leading to buildup of pyrophosphate within the cell, which actually, I believe, overactivates the same system that's associated with hypercholesterolemia. And that's where I think Dr. Weedo and Dr. Lee's paper on the use of statins as a means of helping the system are excellent, because I think that in about 3 or 4 years we're going to be giving a webinar about everything that happens inside the cell, and statins and also excuse me, bisphosphonates are incredible at stopping that problem that happens inside the cell. So to answer the question is yes, absolutely. I think it causes a big problem with the cell. I think it's a big problem ending up being with cholesterol. And I think that in the long run what we'll probably end up doing is our patients with PXE, to take care of some of the cellular problems that happen, is those patients will probably be put on statins.
Wow, great. Okay. And that's something that PCORI, the Patient-Centered Outcomes Research Institute, is looking at too, so there'll be some nice convergences there. Let's see. And this, I think, might be our last question because we're getting, well, we still have 10 minutes, so if there are other questions, please feel free. Could you elaborate on your statement that it looks as though trauma may play a part in developing this? And before you answer that, John, if you think that's, and I think I hear you saying that's a good next webinar, where we'd be very happy to have you pause and not answer that particular question.
I'll answer it briefly, and yes, when I was putting this together, I have a talk that's about twice as long about this, and I realized it was just going to be too much. To answer your question is, I think 100%, is that the best way to think of this is that in health, our tissues are very, very happy. They don't have the problems of depositing calcium and phosphate. Where calcium and phosphate tends to be deposited is in areas that are damaged. And we know this from our work that we're doing on heterotopic ossification, in that we can set up a mouse or even a human to make it so they should calcify their soft tissue no matter what. But if we don't injure them or they don't get injured, it doesn't happen. And so the thing is that the work that we're doing right now is focused on mechanisms including ABCC6 and EMPP1 as seen here, but also other mechanisms that I did not bring up in here that cells make to protect themselves when they're injured. And that's something, that would be what I would want to give the next webinar on.
Well, we're going to definitely book you. Okay, next question. Someone's stating that they have a problem with most statins with elevated chest pain, with elevated CK, pains in muscles, etc. Do you think that there's any connection between that and PXE?
I'm sorry, the question was they have a problem with statins?
Yeah, with most statins.
Oh, that when they take them they have those problems?
Yes, so with taking statins they have those.
Yeah. Unfortunately, some people do have that side effect of taking statins, and that's going to be something more for the, in particular, cardiologists to answer that question, is that there's different formulations that can have different side effect protocols.
Okay. And then maybe the last question. So are you preventing calcification or are you removing it in the mouse model?
That is a fabulous question. So in this picture that I showed you, we are preventing. And the ones that I would talk about in the next webinar would be the ways that we're developing to get rid of it. So the bisphosphonates, we have proven in this system, if I give bisphosphonates to this mouse after it's already developed calcification, I can make it so it doesn't make more calcification, but it will not make this go away. Whereas if I give it to the mouse before it has its calcification, it does this. But we are starting to learn the mechanisms as to how we can try to force the body to make existing calcification go away. That's going to be harder, but that definitely is the place that we need to go.
Okay. Well, John, fabulous job. Perhaps one of our best webinars. Really, really appreciate this. We had everybody stay through the whole webinar, which isn't something that always happens. Lots of comments coming in saying people really appreciated this. I'm sure this archived webinar is going to get a lot of hits. And Terry will work with you on setting up another time for a second webinar.
Well, great. I appreciate the opportunity.
Thank you. So right now, hopefully on our screen, you all can see that we do have all of our webinars archived, and sorry, just a little distracting here. And the webinars are, we'll send you a link for the webinars because I think we're having a little technical difficulty. And then we want to also let you know that we continue to schedule these webinars, as I just mentioned, and we will get back to all of you via all of our usual mechanisms. And then finally, PXE International is in the throes of making sure that we're updating all of the information about you, about your experience of PXE. It's really critical you participate in our survey. Right on our front page, you click sign up, and you can sign up and take the survey. Lots of the questions you just had and lots of the information researchers like John need come to us from the survey, which is self-reported data for now, and then we get the medical records we need, and then we begin those trials and studies we need. So while John's toiling away on working on mice, we want to make sure we've teed up all the people we can find with PXE and tell their story properly so that we do understand what's happening. And we need you to help. We're going for all 4,302 people with PXE. You can see a gauge at the top of the web page showing you how many surveys we have in. Right now we're at 100, so we have a ways to go, and we need every one of you. So again, thank you, John, and thank you to our audience. Terrific questions, and we hope to see you on another webinar.